So, hello everyone again. This is lecture 2 part 2 of wave optics. I am Sameer Lavankar. Let us begin our discussions on refraction theory of wave optics using Huygens principle. So, this is the course outline. We are completed with the introduction part, Huygens principle part, and right now we are in like third part, that is refraction and reflection of plane waves using Huygens principle. So, let us move on to this part only. So, this was the last discussion we kept in the lectures of lecture 2 part 1. So, this was the AB, that is incident wave, this is EC, that is refracted wave, PP dash was the interface given to you, and above the interface was medium 1, below the interface was medium 2, and according to wave theory of light, V2 is less than V1. So, this is the complete concept already known to us. Let us move on to the detailed discussion of how the refraction is being happening. So, please look over here carefully. So, Huygens principle is used to derive the laws of refraction. Let PP dash represent the surface separating medium 1 and medium 2 as shown in the figure. So, this is being talked about here only. So, PP dash is the interface being talked here. Next, let V1 and V2 represent the speed of light in medium 1 and medium 2 respectively. Quite evident, V1 will be the velocity in medium 1 and V2 will be the velocity in medium 2. Moving on. We assume a plane wavefront. Please look over here carefully. The application here is being used to apply the concept of refraction. The wavefront being used is a plane wavefront, not a circular wavefront, not an arch wavefront, not a spherical wavefront. Plane wavefront is used for simplicity. So, we assume what is a plane wavefront? Anything which is passing through a plane is called as a plane wavefront. So, we assume a plane wavefront AB. So, this plane wavefront AB is just to clear you, so just to clear the figure. So, just for more clarity I cleared the figure. So, so this is being done, this is being done, this is being done. So, we assume a plane wavefront AB propagating in the direction A dash A. So, this is the plane wavefront AB, it is propagating in the direction A dash A. So, this is the direction of propagation also given to you by the arrow sign here. So, in the direction A dash A incident on the interface. So, this is the point of incidence at an angle I. So, with the normal the angle of incidence is I. So, hence it is written as small I. So, this is the angle of incidence at an angle I as shown in the figure. Let tau be the time taken by the wavefront. So, let tau be the time taken by the wavefront to travel the distance BC. What is the distance BC here? BC is this distance. Quite evident that BC will be the distance which is equal to speed into time. Speed here will be the velocity in the first medium. Hence, what we can say, BC is equal to distance into time, and this is V1 which is the velocity, sorry, distance is equal to speed into time is equal to V1 into tau. So, BC is equal to V1 into tau. So, we are making the incidence in such a way that the value of BC is 0 and the incident wavefront is in the form of like this. So, the distance AB is such that BC is 0 and BC is 0 and the angle of incidence from A propagating from A dash A is at an angle of I. Now, let tau be the time taken by the wavefront to travel the distance BC. So, quite evident, tau is the time taken by the wavefront to travel distance BC. That is only why when if something is written is here, then with the velocity of V1 at tau this time it will reach point C. Thus, BC is equal to V1 tau, as I already explained you in the above here. Moving on to next slide. In order to determine the shape of the refracted wave. So, final use of this complete concept using Huygens principle is we need to find out the refracted wavefront, how it will be visible. So, in order to determine the shape of the refracted wavefront, we draw a sphere of radius V2 tau from the point A in the second medium. So, now at this point we will assume a secondary disturbance being formed, and from this, so final concept of using Huygens principle is what? We need to find out the wavefront at some t is equal to tau. So, at t is equal to tau, what will happen is the wavefront will be formed, but this time the velocity used in the wavefront's radius will be applicable depending on the medium. So, this time when the sphere will be formed from point A, the processing of this or the waves emanating from this source, this secondary source A will have a velocity of V2. That is why the radius in this case will be V2 into tau. Tau is the time, time is not time is independent thing, it does not depend on anything. It can be not, it can't be tau 1 or tau 2, tau is tau only, tau is time, time is evident for now, but the velocity V2 can change. So, because the wave is propagating in medium 2, we are assuming that the velocity the radius will be V2 into tau. So, in order to determine the shape of the refracted wavefront, we draw a sphere of radius V2 into tau, V2 into tau is given to you from point A, in the second medium. The speed of the wave in the second medium is V2, quite evident, already given to you in the first slide only. Let CE represent a tangent plane drawn from point C to the sphere. So, now C, let also we will make a tangent, such that we will make a tangent to this sphere, we will make a tangent to this sphere such that there is a point such that the tangent passes through C. So, there can be many tangents, there can be one tangent like this, there can be one tangent like this, there can be one tangent maybe like this, but there will be one tangent which passes through point C. So, we need to find that tangent. So, that is a simple means a geometrical construction would be required for that, but after we find that complete tangent. So, let C represent a tangent plane drawn from point C onto the sphere, then AE is equal to V2 into tau. So, what is the AE here? A is this, A is quite evident, I already told you the radius will be V2, that is the velocity in the medium 2 multiplied by the time taken, and CE would represent the refracted wavefront. So, CE, this is how we will get the refracted wavefront. So, just to iterate to you the complete procedure again, first of all there will be an incident wavefront passing through this point. So, what we know first of all is we know that there is a ray of light coming propagating in the direction A dash A. What we also know that it is at an angle of incidence I. Now, what we will do is we will make a wavefront. The wavefront will be such that the value of B C will be V1 into tau. So, now after it quite evident that the direction of this and this will be parallel. So, we will make it, so maybe for construction we can make several lines like this which are parallel to A dash A, and then from a point V1 into tau we will make a line such that it is such that the perpendicular from this line passes through point A. So, this is the complete construction of the incident wavefront. After the incident wavefront is successful, what we will do is we will make a sphere or a sphere of radius V2 into tau. So, now we have a sphere of V2 into tau, and then we will try to find out a tangent plane which passes through point C. So, after this is being formed, this is the incident wavefront, this is the refracted wavefront, and hence we find out the refracted wavefront using the principle of Huygens. So, this was the complete procedure I reiterated to you. Moving on, so then AE is equal to V2 into tau and CE would represent the refracted wavefront. So, refracted wavefront is known to us now. If we now consider triangles ABC and AEC, just to make to you what are those triangles, just let me change the color. So, this is ABC, and this is AEC. This is ABC, this is AEC. Now, what does it say is, we readily obtain sin I is equal to BC by AC. So, quite evident that if this is I, this is 90 minus I, and if this is 90 minus I, I am talking about this portion, this is 90 minus I, and if this is 90 minus I, then this is again I. So, now if this is I, then using the simple principle of trigonometry, sin I is nothing but BC by AC. What is BC here? BC is this portion and AC is this portion here. So, sin I is BC by AC, BC by AC. So, from the principle already assumptions being allotted in the last slide, we got to know that BC was nothing but V1 into tau, and AC was given to you, let AC be AC only, and next was, let me write the sign of R here. So, sin R, again this is, if this is R, then by simple mathematics what we can find is this value is also r. So, this will be 90 minus r, this will be 90 degree here. So, a angle CAE will be 90 minus r, as angle AEC is 90 degree, hence the summation should be 180 degree, hence this value of a angle ACE will be r. So, so finding out now sin r will be again AE by AC, as A is given to you as V2 into tau by AC. Therefore, from this simple equation, let me write this equation as 1, let me write this equation as 2, we will find that sin I by sin R is equal to V1 by V2. So, this is one of the relation we found by using refraction concept using Huygens principle. So, just to iterate to you this line what is written here, if we now consider triangles ABC and AEC, this is a triangle ABC, this is triangle AEC, we readily obtain sin I is this value, sin R is this value, where I and R are the angles of incidence and refraction respectively. So, angles are the similar which are also been explained in the ray optics chapter. So, moving on to the next slide now. Thus, we obtain sin I by sin R is equal to V1 by V2. So, quite evident, as we already talked in the last slide only, that sin I by sin R is equal to V1 tau by AC divided by V2 tau by AC. So, AC gets cancelled, tau gets cancelled, therefore, sin I by sin R is equal to V1 by V2. So, this is the concept we found using this principle. Now, from the above equation we get the important result that if R is less than I. So, if R is less than I, that is the ray bends towards the normal. Just to explain to you clearly what it is talking about here is, let us suppose this is the interface being talked here. Let us suppose this is the interface. If I make a perpendicular to this interface, this is called as normal, this is called as normal. Now, let us suppose I draw a line, let me change the color for more clarity. So, let me draw a line like this, let this be the angle of incidence. Now, what it is saying is if R is less than I, so there can be on refraction either the incident ray can go towards the normal or it can go away from the normal. Let me make both. So, this is the original path, let the green line shows that the incidence the refracted ray goes towards the normal, and let me change the color to let us say purple. So, this color shows that this line shows that the refracted ray goes away from the normal. So, there will be two angles of incidence being formed. Let us say this is the first angle of incidence denoted by R1, and let this be the angle. Always remember the angle is being calculated from the normal line only. So, let this be R2. Quite evident that let me write here. So, R1 is less than I is less than R2. So, if we are going towards the normal, then R1 is less than I, and if we are going away from the normal, then R2 is greater than I. So, if you are going towards the normal, then R1 will be less than I, and if you are going away from the normal, then R2 will be greater than I. So, quite evident, if it is being talked about as R less than I, then it is quite evident that the concept talked about here is towards the normal, that is ray bends towards the normal. So, just to explain to you this line, I explained you to using this diagram. So, now thus we obtain is completed. So, now from the above equation we get that the important result, that is if R is less than I, that is the ray bends towards the normal, the speed of light wave in the second medium will be less than the speed of light wave in the first medium. So, just to explain to you what is written here, if R is less than I, as the angle of incidence and angle of refraction can only be less than 90 degree, therefore, So, this line is being explained here directly using mathematical analysis. So, now from the above equation we get that the important result is if r is less than I. So, if r is less than I, using the mathematical simple trigonometric principles, that if the angle of incidence and angle of refraction is less than 90 degree, then sin r will be less than sin I. Just using the inequality principle we get that sin I by sin r will be greater than 1. We know from the above equation that sin I by sin r will be equal to V1 by V2. So, V1 by V2 will be greater than 1. Again using the equality equations we can get that V1 is greater than V2 or V2 is less than V1, that is the speed of light in the second medium will be less than the speed of light in the first medium. Hence, this is proved. That what is proved, that the wave theory of light can prove that the velocity of the second medium on refraction, if the ray of light bends towards the normal, then the velocity in the second medium will be less than the velocity in the first medium. So, hence this thing is proved. So, let us move on to the next point here. So, now this prediction is opposite to the prediction from the corpuscular model of light. So, this was the model of light which was being explained by Descartes. So, this prediction is opposite to the prediction of the corpuscular model of light, and as later experiments showed, the prediction of the wave theory is correct. So, prediction of the wave theory was correct, hence more research was being done and we got to know the phenomena of diffraction and interference and polarization in wave theory. So, this was one of the major point also. Proof is also done, this point is also done. Finally, now if c represent the speed of light in vacuum, then n1 is equal to c by v1. So, what is n1 and n2? n1 and n2 are the refractive indices. So, the letter used to denote the value of refractive indices is known as n. So, n with the subscript 1 denotes the refractive index of medium 1, n with the subscript 2 denotes the refractive index of medium 2. So, n1 is equal to c by v1 and n2 is equal to c by v2 are known as the refractive indices of medium 1 and medium 2 respectively. So, this is just a mathematical analysis, mathematical thing, you just need to remember this formula. Next, in terms of refractive indices, one of the above equation can be written as n1 sin I is equal to n2 sin r. So, how does this come is, let us suppose we have these equations. So, we have n1 is equal to c by v1, n2 is equal to c by v2, n1 is equal to c by v1, n2 is equal to c by v2. So, now using, let us say I write this as equation 3 and 4, then n1 by n2 is equal to v2 by v1. So, the ratios of the refractive indices are the inverse ratios of the velocities. So, from the last equation what we know is v1 by v2 is equal to sin I by sin r, that means v2 by v1 will be nothing but sin r by sin I. So, using this equation what we will get is n1 sin I is equal to n2 sin r. So, what we can infer from this equation is, so just to explain to you, this is the only equation written here. So, n1 sin I is equal to n2 sin r. Just to remember this, what we can say is, what is the angle of incidence, what is the angle of incidence or any angle being formed with a normal in medium 1 is I, any angle formed in medium 2 is r. So, sin r, what will it be multiplied with? The refractive index of medium 1 only. So, n1 sin I, sin r will be multiplied to something, what it will be multiplied with? The refractive index of medium 2. Hence, the equation is quite easy to understand and quite easy to remember also, that is n1 sin I is equal to n2 sin r. So, this is known as the Snell's law of reflection. So, this is known as the Snell's law of refraction, this is known as Snell's law of refraction. So, let me conclude the complete concept till here only, because after this the wavelength concept will be introduced. For now what we studied is, we studied the concept of how the incident wavefront gets changed into refracted wavefront, and finally using the equations of some trigonometric analysis and some equalities of triangles, we got to know using sin I and sin r equation, that sin I by sin r is equal to v1 by v2, and as we know that for I less than r, the velocity I less than r, when we calculated using the methods of inequality, we found out that the velocity in the second medium will be less than the velocity in the first medium. Hence, the wave optics theory is being analogous to the real life example of equations or sorry analysis we found or the velocity we found in real life for water and air interface of one of the experiments. And finally, using the concept of refractive indices, the final equation which we formed is, which you need to remember, is n1 sin I is equal to n2 sin r. For now, let me close this lecture here only. In the next lecture, we will start with similar concepts of applying the wavelength into this equation, and then we will move on to the reflection part, reflection law of wave optics, wave theory using Huygens principle. So, for now, thank you.